A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Students, today we are going to do synthesis of aromatic compounds, SNAR. The key concepts which we are going to discuss in this lecture are, first of all, the introduction of nucleophilic aromatic substitution, then mechanistic approach, like how should we think mechanistically, then nucleophilic aromatic substitution by the SN1 mechanism, then reagents for aromatic nucleophilic substitution on aryl diazonium, then ortho and para product mixtures. Nucleophilic aromatic substitution. A nucleophilic aromatic substitution is a substitution reaction in organic chemistry in which the nucleophile displaces a good leaving group such as a halide on the aromatic ring. You can see the example on the right hand side. Benzene ring having leaving group X is halogen or anything like that, and nucleophile is just attacking and is displacing this halogen, and then as a product nucleophile is attached on the benzene ring. There are 6 nucleophilic substitution mechanisms which are encountered in aromatic systems. Number 1 is SNAR, addition elimination mechanism. The most important of these is the SNAR mechanism, where electron withdrawing groups activate the ring towards nucleophilic attack. For example, if there are nitrofunctional groups, position ortho or para to the halide leaving group. Now you can see the lower one example, the benzene ring is having halogen, but it is also having an electron withdrawing group attached with it. So the nucleophile will come. In the first step, it will be attached, like you can see the sigma complex. This is called the addition reaction. And in the second step, the leaving group leaves and the nucleophile then attaches with the retention of the aromaticity, or aromaticity is regained in this step. So this is the elimination step, the second one. The aromatic SN1 mechanism encountered with diazonium salts. This is the second type of mechanism. The SN1 reaction is a substitution reaction in organic chemistry. SN, you know, that stands for nucleophilic substitution, and 1 means that as the unimolecular reaction, that the rate determining step is unimolecular. You can see an example of aromatic SN1 mechanism on the right hand side, like benzene ring is having a diazonium and N2, diazonium and 2 diazo, 2 nitrogens. There is a triple bond in the nitrogens, N triple bond N. So at the positive charge, the central nitrogen is having 4 bonds, so it will be positive. But this diazonium compound will and nitrogen will be removed from this diazonium compound, and aryl cation as a result will be formed, and the nucleophile will come and thus will be attached on the, or it will just attack on the aromatic ring and will be attached. Third type of mechanism is benzene mechanism, E1CB ADN. Arynes or benzenes are highly reactive species that are derived from aromatic ring by the removal of 2 substituents. So you can see the benzene on the right, the lower one example on the right hand side is the benzene mechanism. What happens in this mechanism? There is a chlorobenzene with action of sodium-iodine liquid ammonia. The chloro has been removed from here, and also 1 hydrogen is also removed from here. So as a result of removal of the hydrogen and chlorine, a triple bond is formed here on the benzene. So that is called benzene or aryne. So, and then there will be there will be an attack of the nucleophile, and that can come at the position and can be attached on any one of the carbons having a triple bond. So both can be options. The NH2 can be attached on any one of the triple bonded carbons. So there are other mechanisms also. The free radical the free radical SRN1 mechanism, the NANRORC mechanism, the vicarious nucleophilic substitution. These are not very common mechanisms, but the very common, and that will be again and again repeated in the retrosynthesis, are the above three nucleophilic substitution mechanisms, which I have discussed briefly. Nucleophilic aromatic substitution. If we make the same disconnections as we have done before, like for 25, 20 and 27, right? But we change the polarity, we need electrophilic aromatic rings, the nucleophilic reagents. पहले हम कर रहे थे पिछले लेक्चर में electrophilic substitutions कर रहे थे, we were thinking about the electrophiles. अब हमने reverse करना है. We are changing the polarities. What are we changing? Now we are in need of electrophilic aromatic rings and nucleophilic reagents. Reagents आपकी बाहर nucleophilic होना चाहिए और rings जो है वो electrophilic होना चाहिए. We shall need a leaving group X on the aromatic ring like 26. And reagents such as alk oxides or amines. हमारे पास nucleophiles होने चाहिए. For example, हमने 25 को disconnect किया, so we shall be having a nucleophile like OR negative, and we shall be having an electrophilic ring like aromatic ring having a good leaving group or halogen, that is electron withdrawing and making the aromatic ring electrophilic. And similarly 27, if we are doing the disconnection, the NR2 should be a nucleophile, like it should be like an amine, and the aromatic ring again should be a bit electrophilic. Now the nucleophilic reagents are behaving normally for alcohols or amines, but the aromatic electrophiles present a problem. So it is very right, like if we can have aromatic nucleophiles, that is fine with the alcohols and amines, they can be nucleophile. But for benzene ring to be electrophilic is a bit to be electrophile, like is a big problem. Like benzene rings are nucleophilic, they are weakly, but they are not electrophilic at all. So what to do with that? Like you can see the example, the reactions given below, the OR, like nucleophilic, if suppose it is alcohol or alk oxide or whatever is that is attacking on the aromatic ring, and the aromatic ring is having a nitro group and good leaving group chloro. So it will attack on the position where there is a good electron withdrawing group like chloro, and it will will be added, as you have seen before, addition elimination. When it will be added, this nitro will be then making that charge, which is due to the attack of nucleophile, which will be stabilizing the charge. Any electron withdrawing group can stabilize that charge. So 28 is on 28 there is an attack of nucleophile, and 29 the negative charge is stabilized and there is a resonance, and then 30 that leaving group leaves and the nucleophile attached on the aromatic ring. So we can be guided in our choice of polarity by the nature of the target molecule. Now if we see that the Lilly pre-emergent herbicide trifluralin B31, it has 3 electron withdrawing groups, 2 nitro and 1 CF3, ortho and para to the amine, ideal for the nucleophilic substitution on 32. Now suppose if we are saying that there is a compound 31, it has 3 electron withdrawing groups, and if we go towards the disconnection and we see that synthetic equivalent 32, So we can think about the synthetic equivalent 32, which is having 2 nitro groups and 1 CF3 group. So in the place where there is some nucleophile like amino isopropylamine, that we must have to think about the chloro. Electrophilic aromatic ring. How can this be an electrophilic aromatic ring? This can be an electrophilic aromatic ring if we consider good electron withdrawing groups attached to that. So, and at the place where there is a nucleophile, but we are disconnecting the nucleophile and the electrophilic aromatic ring. So at the place of that nucleophile, there must be a good leaving group. So we have thought of chlorine, which is attached with the aromatic ring in 32. Then this one, the 32, can come from simply the nitrogen of this 33 trifluoro, and there is a trifluoromethane and there is a chloro para to that. So now simply the synthesis simplicity itself as the synthesis of any agrochemical must be like the base in the second step is to remove HCl produced in the reaction, not to deprotonate. I mean, like what are they saying? They're saying like 33 is nitrated to produce 32, then 32 is reacted with this isopropylamine to produce 31. Now they are saying that the base in the second step is just used to remove the HCl. What HCl? The HCl which has been produced by the reaction of this isopropylamine and this leaving group Cl. The HCl was produced to neutralize that HCl. The base is being used. So it is obvious that the choice between nucleophilic and electrophilic substitution must be mechanistically made, but this is generally true for the choice of all the disconnections for all the syntones and reagents. We should go mechanistically. Like in the previous slide, we have done the synthesis of the formation of 32, and that was easy because the aryl chloride was activated by 3 electron withdrawing groups for nucleophilic substitution. Now look at another example. In the synthesis of fluoxetine, Prozac, a rather widely taken antidepressant, aryl ether 34, that is an essential intermediate. Though disconnection B looks attractive as this will require only simple SN2 reaction. But disconnection A was preferred. Why? Because 32 must be a single enantiomer, and we can get the enantiomerically pure alcohol 36, which is available. And if we disconnect, if we do the disconnection A, so we can make up 34 by nucleophilic substitution. By using nucleophile 36 and electrophilic aromatic ring 35, which has been made electrophilic by having a strong electron withdrawing group, trifluoromethyl group. So, but fluoride is the worst leaving group among the halogens, as the C2F bond is very strong. We all know that. So, but it is rare to see an SN2 reaction with fluoride as the leaving group. Nucleophilic substitution reaction bimolecular with the fluoride group as the leaving group, but it is the best choice for nucleophilic aromatic substitution, especially when the ring is only weakly activated. The reason is that in the nucleophilic aromatic substitution, first addition of the nucleophile takes place and then elimination takes place. So fluoride is removed, the leaving group is removed after the attachment of the nucleophile. But in the case of SN2 nucleophilic substitution bimolecular, what happens? Then what happens? But in normal cases, not for aromatic, but in normal SN2 reactions, the fluoride is the worst leaving group, because in normal SN2 reactions, at a bimolecular reaction in which first there is a bimolecular reaction, there are two molecules which are involved in the rate determining step, bimolecular reaction. Attack of the nucleophile and removal of the leaving group will be at the same time. And fluorine and carbon C to F bond is very strong. So as a bond is very strong, so it is not a good leaving group. So it is really SN2 is seen with the fluoride as a leaving group. But for aromatic nucleophilic substitution, it is excellent. The reason is that, and especially when the aromatic ring is not highly activated, like in the case of 35. This fluoro group, strong electron withdrawing inductive effect of the fluoro, will make this position very potent for the nucleophilic attack. So that's why that is very best for nucleophilic aromatic substitution. Now, this is a two-step reaction. I have explained a bit in the previous slide. This is the difficult step is the addition of the nucleophile. The aromaticity is destroyed when the nucleophile is added, and the intermediate is an unstable anion. So if there is an electron withdrawing group that can stabilize that anion, then this reaction can happen, aromatic nucleophilic substitution. Now, the second step, 38, is the first, when the leaving group leaves. Fluorine accelerates the first step as is so electronegative, and it does not matter that it hinders the second step as it is a first anyway. So, as I have explained in the previous slide, so from the attack of alcohol on the aromatic ring, 38 intermediate, which is anion is formed, which is stabilized by the resonance, and then the second step is the leaving of the fluoride ion. The formation of the trifluorylene 31 showed that amines are good nucleophiles. For nucleophilic aromatic substitution, in the nucleophile here is an amine alcohol 36. As we have seen that the formation of 31, that amines are good nucleophiles. But here is the nucleophile is an amino alcohol 36, which is shown over here. But right now, what we have to do, if the direct reaction of 36 might lead to the formation of an amine instead of an ester, we need an ester. We need to make an ester 38 as an intermediate, and finally just we need an ester. If we want to make an ester, the alcohol must attack on the aromatic ring. But the direct attack of the 36, this alcohol, amine alcohol, can make an amine as a result of a nucleophilic attack. In the case when N will attack on the aromatic ring. So to avoid this, first 36 is treated with sodium hydroxide to make the oxyanion and then added to 35. So the alcohol is less nucleophilic, but the oxyanion is more nucleophilic than the amine. Otherwise, alcohol and amine will compete, and amine is more nucleophilic. And alcohol, why amine is more nucleophilic? Amine is more nucleophilic. There is only one lone pair, and oxygen is having two lone pairs. So there is a competition between these two lone pairs, which make it less nucleophilic as compared to nitrogen. So amine is more nucleophilic, but when we pick up a proton from the alcohol will be the oxyanion will be produced that is more nucleophilic than amine. So we treat 36 with sodium hydroxide to make it more nucleophilic. Nucleophilic aromatic substitution by the SN1 mechanism. Now, how the SN1 mechanism takes place. SN1 mechanism means unimolecular nucleophilic substitution. Unimolecular nucleophilic substitution means that there is only one molecule in the rate determining step. It does mean the leaving group leaves first and then the attack of nucleophile takes place. Now, though the SN2 mechanism is not available for aromatic nucleophilic substitution, the SN1 is providing, we use the very best leaving group available. So if there is a very good leaving group, then what will be that it can leave and it will make the aromatic ring as a there will be a positive charge will be generated on the aromatic ring. Now this is a molecule of nitrogen which is released from a diazonium salt 42. So you can see that on the 42 and in diazonium salt, nitrogen, triple bond nitrogen, the central nitrogen will be positive due to making 4 bonds. On gentle warming, the 42 will release N2 and will be converted into a cation. A standard sequence is nitration of an aromatic compound 39 to give 40. What happens when first of all we do the nitration? 39 will be converted into 40 after nitration. Then the reduction of that nitro group will take place using hydrogen over palladium in charcoal or tin chloride. So, in diazotization then after the amine formation, diazotization with sodium nitride over HCl will give diazonium salt 42. That reaction takes place at low temperature like 5 degrees centigrade or lesser than that. Nitrous acid HONO is the true reagent giving nitronium ion that attacks at nitrogen. Now the diazonium salt 42 is stable at 0 to 5 degrees centigrade, but it decomposes to N2 and an unstable aryl cation 43 on warming to room temperature will be formed. So we can see that here 42A, by the removal of diazonium N2 above 10 degrees centigrade, there will be a cation, aryl cation will be generated, that is 43. The empty orbital of 43 is an sp2 orbital in the plane of aromatic ring, quite unlike the normal orbital for cation like 20. As we have previously seen, now this cation, this positive charge, this is just an sp2 orbital in the plane of the aromatic ring, which is a cation. So what will be, there will be a nucleophile will be approaching over here, and 43 will be converted into 44 after the attachment of that nucleophile. Then proton will be removed and 45 will be there after the nucleophilic substitution. Now again we can check that this route nucleophilic aromatic substitution by the SN1 mechanism is particularly valuable for the substituents that cannot easily be added by electrophilic substitution, such as OH or cyanide. For the addition of cyanide, chloro, bromo, cuprous derivatives usually give the best result. So the aryl nitrile 46 might come from amine 47 via diazotization. So we can take 47, we just do the disconnection of 46 at cyano group and aromatic ring, and then we can assume the synthetic equivalent 47 amine. Then we just get that amine from the reduction of nitrous, so we can do the FGI, the 48. The synthetic equivalent 48 is the equivalent from which we can get 47. Then that 48 can come from toluene, that by the electrophilic substitution. So the route can be, this is straightforward. In the laboratory, you would not have to carry out the two first step, as the amine 47 can be purchased. Very simple. So we do not draw the diazonium salt. So you can, if you want, but it is usual to show the two steps carried out without isolation of the intermediate in the style 1A and and in the 2 the reagent B. Now you can see that toluene compound 5, nitrated we got 48, then reduced we got 47, then diazotized, and then it was treated with cuprous cyanide, then we got 46. Now as far as reagents for aromatic nucleophilic substituents are concerned, a table is given here after the reaction. As we know that the aromatic nucleophilic substitution starts from an amine, primary amine, that is diazotized. 41 here is shown, structure number 41, that is diazotized at 5 degrees centigrade, and then after the diazotization 42 intermediate is formed, and then reagents, whatever the nucleophiles are there, they attack, and then 49 is formed, that is the attachment of that nucleophile and the removal of N2 gas. Now if you want to show the disconnection zone 49, for example, the synthons which can be formed are OH, OR, that can be substituted in the place of Z, OA in 49, and the list of synthons I am just going through: OH, OR, cyano, chlorobromoido, aromatic H, simple H. So the reagent for these can be water, alcohol, cuprous cyanide, cuprous chloride, cuprous bromide, potassium iodide, aromatic compound, can be benzene even, and then phosphoric acid or ethanol or H positive. Ethanol in the acidic medium. Now for all of these some commands are given: water and hydroxyl water and alcohol. When the reagents are used, this is probably a SN1 reaction when there are reagents like cuprous, cyanide, chloride, bromide, that can be a radical reaction. Potassium iodide, that is the best way to add iodine, Friedel-Crafts relation, the second last one, and that is the Friedel-Crafts relation means adding aryl group along with the aromatic system, along with the aromatic ring in the place of C. So, and then the last one is the reduction of diazonium. Means in the reduction of diazonium, what we do, when we do reduction of diazonium, this N2 will be reduced. So that will be substituted by hydrogen in the presence of phosphoric acid or acidified ethanol. Here the discussion of two products, ortho and para mixture, is discussed here. When we do the nitration of toluene, both para-nitro, that was shown in the structure 4 para-nitro, and ortho-nitro compounds are formed. In fact, the reaction gives a mixture. So this is acceptable because providing these compounds can be separated, especially if the industry does a job on a very large scale, as here, like in the synthesis of a sweetener, saccharine. That is a good example for that. Saccharine compound 50 is a cyclic imide, that a double amide from one nitrogen atom and two acids. That is double amide from there is a one nitrogen atom and there are two acids which are making bond with that nitrogen. If we disconnect C2N bond and S2N bonds, the two acids, one carboxylic acid and one sulfonic acid are revealed. Structure 51. Now FGI convert one of them into ortho-para directing groups, and we can use the same oxidation reaction we met at the start. So now 52 can be made by sulfonation. What did we do? If you remember that when we were going to disconnect the the benzoic acid in the previous slides we have seen, we did say that disconnecting the C to C bond of the carboxylic acid is not a good reaction. It will not give a good reaction to construct this benzoic acid. So what we do FGI. We did FGI at that time also. Then we have produced the benzoic acid or carboxylic group on the aromatic ring by the oxidation of methyl. So we can take toluene. So now if we do the disconnection of C2S bond in 52, we can get this from 50. We can get this 52 from toluene. We can do the sulfonation of toluene, and we can get 52. In practice, chlorosulfonic acid is used as this gives the sulfonyl chloride directly. So now if we are thinking that chlorine might be the best leaving group, so but there is no Lewis acid here, so instead a very strong chlorosulfonic acid protonates itself to provide a molecule of water as leaving group. So from what can we do from the toluene? The toluene can be reacted with chlorosulfonic acid to give 53 sulfonation. Chlorosulfonyl group is added, and then two isomers have been formed, ortho and para. Now the thing which I have mentioned here, that chloro is a good leaving group, but in the case when there is no Lewis acid here, so this will not leave like that. So chlorosulfonic acid protonates itself to provide a molecule of water as leaving group. So now here water is removed from here, and the replacement of H from here and OH from chlorosulfonic acid will remove water from here, or from full of the reaction I am talking about, but actually chlorosulfonic acid ClSO2OH, OH from here and H that is used for the protonation of chlorosulfonic acid. The water will be removed from here first, and afterwards the full reaction is the replacement of hydrogen by chlorosulfonyl group. Now the reaction gives a mixture of ortho 53 and para 54 plus ortho-para. The ortho compound. The ortho compound is converted into saccharine by the reaction with ammonia. So if we do the reaction of 53 with ammonia, then that Cl is replaced by ammonia. Then if we do the oxidation of the reaction of with ammonia and oxidation and the para compound toluene sulfonyl chloride 54 para compound, that is toluene sulfonyl chloride 54 orthosyl chloride, is sold as a reason for converting glucose into leaving groups. So there is no way we can get this 53 by this route. The para compound, the toluene sulfonyl chloride is actually orthosyl chloride. Para compound, toluene sulfur alcohol 54. The tosyl chloride is common in it is it will be used for the in the market as a reagent for converting alcohols into living groups, and 53 will be converted by the reaction with ammonia into 55, and then will be oxidized with the KMnO4 to give 56, and then will be heated to give the imide 50, that is saccharine.